Hi there, my name is Cristian and I'll be presenting our paper, Quantile QT-Opt for risk-aware vision-based robotic grasping. This is a joint work with my wonderful collaborators from Google X and Brain. The distributional perspective on reinforcement learning has given rise to a series of powerful Q-learning algorithms, resulting in state-of-the-art performance in arcade game environments. However, despite the improvements brought by these methods, it is yet to be determined how they scale up to challenging real-world applications with continuous action spaces, such as vision-based robotic grasping. Besides the possible performance improvements, distributional RL methods could also provide a way for robots to achieve safe control in the face of uncertainty. To answer these questions, in this work, we propose a distributional version of QT-Opt, a distributed Q-learning algorithm for continuous action spaces, known for its unique demonstrated scalability and real-world generalization performance. We call our method Quantile QT-Opt, or shortly Q2-Opt. Unlike QT-Opt, which learns the expected return for a given action, Q2-Opt learns an entire distribution over these returns. This distribution can capture the uncertainty of the returns generated by the stochastic environment dynamics and the unstationary training policy. The additional information encoded by the distribution can be used to quantify the risk of the possible actions and consequently take better informed decisions. To learn this distribution, Q2-Opt approximates its quantile function at certain location on the unit interval encoded here by the vector tau. Then, the policy attempts to maximize the scalar aggregation function psi, which computes the mean of the vector-valued function q. Q2-Opt comes in two flavors, based on the previous work on QRDQN and implicit quantile networks, respectively. The difference between these is given by the type of vectors they take as input. The first method, Q2R-Opt, always approximates a fixed tau corresponding to the quantile midpoints, which are illustrated here by the gray dots. In contrast, Q2F-Opt learns a quantile function and can therefore be evaluated at any arbitrary location on the unit interval. To investigate how robots can manage risk in practice using distributional RL, we leverage the additional information supplied by the value distributions. Similarly to Dabney et al., we use a risk distortion function to transform the uniform samples and obtain a spectrum of risk-sensitive policies. Concave functions produce risk-avoiding behaviors, which effectively put more weight on the lower quantiles of the distribution, while convex functions generate risk-seeking policies, which pay more attention to the higher quantiles. For our experiments, we adopt the QT-Opt architecture and modify only the size of the output layer to make the Q network multi-headed. In simulation, the distributional methods achieve higher grasping rates than QT-Opt, both as a function of the number of training steps, as seen on the left, and the number of scene episodes, as shown on the right. When considering risk-sensitive policies in the same setup, we observe that risk-averse policies, the last 4 entries in the table, increase the success rate even further. In the real world, we trained the model offline from a 72 TB dataset of real-world experiences collected over 5 months from a mixture of QT-Opt and scripted policies with random exploration. Given the chaotic nature of real-world interactions and the multitude of policies used to collect the data, this is an ideal setting for distributional RL. To showcase our setup, we include a video from the robot's camera and an overlay of the predicted value distribution for the selected actions. The results on the right show that while the model order from simulation is largely preserved, distributional methods and especially risk-averse policies are better than our baseline by a much higher margin. Besides the performance improvements, we noticed risk-sensitive policies exhibit distinctive behaviors, even though they are trained from the same data. This video example shows how the risk-averse conditional value at risk policy learns how to use the edges of the beam to become certain that it has grasped the object. To illustrate this point further, the plot on the right depicts the number of broken gripper fingers for each method during our real-world evaluation, ordered from risk-averse to risk-seeking. This data shows that risk-averse policies implicitly achieve safer interactions with the environment. Finally, in an attempt to replicate the latest batch RL findings from the arcade environments, we perform an equivalent study in our simulation. We consider 3 types of batch RL datasets: the replay buffer of a QT-Opt run, data collected by a random scripted exploration policy, and data collected by an almost optimal policy. Unlike in the previous work in discrete environments, unfortunately, we do not notice any significant improvements from the distributional RL methods in any of these settings. A distilled version of our paper containing many additional videos can be found on our website. Thank you for your attention.